mounted on a monument, what we call a monument, which is deeply pressed into a rock outcrop. Basically, the point is that if the ground moves, your GPS antenna will move. We are going to be tracking millimeter scale motions. So these stations also have solar panels for to be able to look up to power all the electronics and an equipment enclosure that houses the receiver, the batteries, and a host of communication devices and perhaps other geophysical instrumentation. Next one, please. So the high precision GPSs currently gives you accuracies of sub-centimeter. We are capable of getting repeatabilities in the order of 1 to 2 millimeters. We are using multi-frequency receivers as opposed to a consumer grade, which only gets one frequency. But for that, we also need high precision orbital information or frame of reference. Our first frame of reference is the satellite position, so we need to know with very good detail where each satellite is at any point. We also use multiple stations, and we use sophisticated processing software, and we also collect lots of data. Whether that's big data or not, that's another question. Next one. So how do we actually locate ourselves? Well, basically, this is you may remember your secondary grade classes where you would look at positioning via triangulation. It's exactly the same thing as you would do, but the only difference is that we're doing it with satellites. We may need a fourth satellite to actually adjust the receiver's time, but basically with 3 or 4 we're able to locate ourselves. Next one. How do we know the distance in order to do this triangulation? Well, the satellite transmits a specific signal, which is connected, and the receiver in your hand or in your car will see that same code, but with a very small time delay. And that time delay is proportional to the distance, and that's what we call a cellular range. Basically, the distance in between your receiver and each one of the satellites. Of course, there's a lot of sources of errors due to satellite orbits or atmospheric delays, depending on the ionosphere, on the troposphere. The amount of water in the atmosphere plays a big role on getting these distances. A little bit of error, and also multipath or also human errors. Next one. What's the next one? Yes, and other human sources of error like this one. Next one. So, global-wide, there's a large number. Currently, we're in the order of about 4,000 stations, which do provide open data access and are for academic purposes. Most of them are freely available, some of them not, but basically, it's a large collection of receivers, of geological receivers distributed all over the world. Next one. So, just to make this a bit more faster, just suffice to know that the first receiver in Mexico was part of INEGI's Red Geofísica Nacional, and the first, a year later, in 1994, the first permanent research GPS in Mexico was installed in CICESA in Ensenada. Next one. From there, we've been going to next one. to the present day, where we have around, we do have 156 continuous GPS stations throughout Mexico. All of these have more or less freely available data, and that is the basis of the research using GPSs in Mexico. Next one. So, in specific, TLALOCNet is a continuous GPS and meteorological network for the study of earthquake cycle, tectonics, ground subsidence, and other atmospheric processes of Mexico. And the interesting thing is that TLALOCNet fills a large gap that existed in between the large networks such as PDO in the northern part of North America and the Central American Caribbean networks such as Cabral. So now we have a continuous network spanning from Alaska all the way to South America of GPS stations. Next one. This is the current map of TLALOCNet stations. Green ones and yellow ones are operational. The red ones are the ones that we are scheduled to install in the rest of this year. Next one. If you add the TLALOCNet to the rest of other GPS networks, including NEGIS, other UNAM networks, and the Servicios Seismológicos Nacional networks, this is the current coverage that we have for GPS. Next one. This is how a GPS station looks like. We have, we've already seen a little bit of that. We have a monument, we have the antennas, and we have all the instruments. If you can go a little bit faster, next one. So telecommunications is a big issue of if we want to use GPS networks for real-time applications. Manual downloads or downloads, periodic manual downloads are okay for doing research. But if you want to use these networks for things like early warning systems or new applications such as atmospheric applications such as water vapor, etc., the telecommunications is just a key issue for this. So what are the requirements to have these stations? The requirements is to have a very good satellite visibility for looking at the GPS satellites, and a little bit of security. We have, and also one of the big things when we scout for locations is the potential for telecommunications. And depending on whether we are in a suburban area, then it's cellular connections work okay. If we are in remote areas such as this example in Baja California, VSATs and satellite links are the only way to go. Other factors are reliable power. Then telecommunications is an issue if we really want to use these systems for future early warning systems where conditions, for in case of, for example, an earthquake, a hurricane, we need high availability, we need low latency telecommunications. Next one. So some of the telecommunication challenges that we face for real time, we have, for example, seen that newly developed programs aimed for internet or digital inclusion can be a great asset for all these geophysical observations. But the collaboration between the Mexican federal agencies who develop this and the academia is going to be a little bit hard to initialize. We are talking about federal agencies may not be that used to these collaborative agreements that we in science are so much used to. Sometimes we talk a different language, and that's also part of our fault that we do not convey the right messages to these agencies. The other challenges are that these, for mid to long-term viability of these networks, the telecommunications fees, the telecom fees, are the single largest cost for our operations and management of these networks. And that, on the other hand, is probably the single most difficult item on your budget if you're putting together a scientific project that you are going to get because operations is it's difficult to get, let's put it this way. We feel like putting into a facilitated role in this situation, and that would help pave the road for more collaborative participations in these federal digital inclusion programs such as Mexico BigData. Next one. Let me show you a little bit about data. Let me show you the just go all the way through that slide. Basically, I want to show you that we have the remote stations. These connect to two data centers. One of them is in Colorado, the other one is in Universidad de Guadalajara, our TLALOCNet data center. And these two are the pickup point for any GPS data that all different users should use. These data centers running in these two locations are completely, they are operating in a federated seamless archive network, which means that you can query for your data in either one of these, and irrespective of where does the actual data resides, whether it's in a hard disk, in UDG, or a hard disk in NAFTA, it will be completely transparent to the user, and you will get your data. This also works very well. We have a fairly robust mirroring scheme in order to prevent any data loss, or also looking into the long-term viability and existence of these assets. Next one. This is the TLALOCNet data center. This is a queryable open data access that includes GPS, MET, and real-time streams to all the TLALOCNet and other contributed GPS networks in Mexico. It's based on GSAC and open source package developed by UNAM, and we are of fairly recent operations. We started last month, and next one. I'll show you some of the metrics of the data center in 1 minute. So the big question is, now that as we are in a session talking about big data, the open question is whether GPS is big data. GPS research in Earth and space science need a fairly large number of data collectors, namely continuous GPS stations, as I showed you, and long-term observations, especially in geodesy, by a large number of these distributed sites, is the core of our GPS research. So, but big data needs big repositories. They should, at least for scientific purposes, we aim to be open and free. So the TLALOCNet data center at UDG is the first Mexican community effort for a perpetual archive of GPS and MET observables using community-based vetted metadata and exchange formats. So this is just to roughly give you an idea. Each station, if it's acquiring at 15 seconds, which is the standard rate for a daily solution, if we assume 10 cellular ranges observations per satellite per epoch, that gives you 55,000 observations per day per station. If a station operates at 1 hertz, like one observation per second, we are talking about 800,000 cellular per station, which is 1 hertz is the standard rate now for real-time GPS. If we want to go to the next step, we want to do 5 hertz, which is the current best rate for seismic geodesy applications, such as earthquakes, for example. We may have over 4 million cellular range observations per station per day. However, this poses some problems. Right now, we're only archiving the 1 to 5 hertz streams are only archived for very small time frames, and especially they are collected under demand, and they are archived just for specific events, such as earthquakes or several. So basically that means that we are throwing away a lot of data and archiving only a very small fraction of the GPS observables. Next one. The TLALOCNet data center, like I said, it's a collaborative effort between UDG and UNAM. It started operations on March. Currently, we're archiving data from 54 of these continuous GPS stations. On average, they hold about 3.5 years per site. And currently, we have over 72,000 file holdings, including observational, navigational, and meteorological files. So far, we're getting 19 gigs of data, and just for these 50-something stations that we have started with. So far, in these last 2 months, we have been serving around 70,000 files to different organizations, both in Mexico, the US, and Europe. Next one. But looking ahead, if we think about all the 156 sites that do exist in place as of today, not including the 21 sites from Mexico, and if we look at the whole historical holdings for all these sites, we should be talking about over 180,000 observational files. And that's around 136 gigabytes of compressed data. Next one. Let me point that these GSAT-based GPS repositories are a community effort. There's a large, so far there's around 16 different GSAT repositories in the rest of America and Europe. So it's so basically that allows us to have a clear idea and operate with the very same metadata formats, data exchanges, everything. All that has been solved so far. The next one, if we look at the GPS data growth perspectives, this is where it starts to get dicey. If we are currently having 156 GPSs, we are funded to grow to around 200 sites in the next 2 or 3 years. But it may sound like a lot to have 200 plus sites, but if you look at what the current geodetic community is doing, it becomes very clear that we're far away. For example, if we are looking at Japan, for example, Japan has around 1,200 of these stations, and when the size of the country, it's about, it's a fairly high density. Same thing with the US. The US has around, just for academic purposes, on the West Coast, it has, PBL has around 1,300. If you add up the NGS course contributed sites, you may be close to 2,000 stations. So if Mexico with for our density, if we want to go and have that sort of GPS density, we may need to grow around 2 or 3 orders of magnitude. Based on the size of our country, we will need in the order of something in between 300 and 3,000 stations of GPS. So we still have a long way to grow on that respect. The other thing is that as things move around, the increasing sampling rate of the equipment is probably also going to play an issue. Right now, our standard is an epoch observation every 15 seconds. However, the actual hardware capabilities can be they can lock at 20 hertz, so that's 300 times more. And we only record at 5 hertz for on-demand large seismic events. That is only for one GPS constellation. So far, we do not have any plans for collecting other GNSS constellations, such as the Polaris, the Russian GPS equivalent, and Galileo, which is under construction, the European GPS system. So if we are looking at archiving 5 years data with 3 GNSS constellations, that means that we will need to increase over 200 times our data focus. Next one. So why are geodetic data, and let me speed up things here. Geodetic data centers are important because we need to reprocess all that collections of data, because we need to do periodic global reference frameworks, new software versions, new satellite orbits, and that means that every 2 years or so we need to process the whole historic collections of GPS data. Next one. And let me jump to the next one, please. Well, so what are the, I just want to spend the last, I know I don't have much time, but I just want to spend the, I want to talk about the big challenges for Mexican GPS data centers. One of them is the scientific. We need fully operational units 24/7, especially if we want to use these systems and if they want to be the core of early warning systems. In the scientific realm, we would like, we generally do not like data gaps in our time series. The GNSS networks are the cornerstone for tsunami, space weather, for the telecommunication people, satellite communication disruptions by solar activity or magnetic activity. It's a big issue. GPS contributes a lot for this space weather. Also, it's a national infrastructure. I would like to put together the fact that early adoption is not coded on the Mexican government DNA. We lag behind many of new technology developments. And GPS network in other parts of the world have become a key part, a fundamental part of the national infrastructure in any country, especially economies comparable to ours are, even if we compare, for example, when we compare to Chile, if we compare to Colombia, for example, the federal operated GPS network is 2 or 3 times smaller than in those countries. So we're clearly far behind. From the technological point of view, we have If we are looking into GPS densification, the last mile connectivity is a key issue. We need fast, high availability and low latency connectivity if we want to use GPS data for main real-time applications. And I also think that the synergy, for example, with Mexico Conectado is definitely something that we would like to see and pursue. I think that CUDI should play a higher profile role and serve as a link in between science applications and the relevant federal government entities, because I think it's one of those few agencies that have a foot on each side of the field. Next one. Well, we have financial. I think that I'm sure that's a challenge for everybody, especially for perpetual archiving. That's an issue. CONACYT is very keen on having these natural repositories developed, but have yet to see a clear funding channel for realizing that goal. And other things which are also very important are the educational. So far, and I'm talking from our perspective, we do not have a formal training or training on best practices for big data creation on archiving. We are scientists and we know our level of expertise may not lie exactly in those areas. And I can see that there's a clear need for having a geoscience and IT technologies opportunities. I think this is an area where we could do much better if IT people, if geosciences and IT people could sit together and look for possible areas of interest. And also the historic values. The GPS observations cannot be reproduced, which means that they have a time dependency, and geologic processes have a very long, they need very long time series for proper analysis or to the insert. And that is just because that's the nature of geology. Geologic processes take a long time, and that far surpasses the human lifetime. So, finally, this is my last slide. I just want to say that I don't know if we are a deep dysfunctional family. The group collaboration is sometimes hard to encourage. There's still very good collaboration in between geoscience and IT areas. And the other thing is that I've been seeing a lot of effort into talking about the Mexican repositories, but they are geared more into the paper libraries rather than data. And I also would like to know whether all these efforts into going into these national repositories are for, I would like to think that they are not fully, they have not fully developed for the advancement of science. I think that there are a lot of things which are also very valid, fiscal responsibility, ethical purposes, and so on. But that's another issue that we'll need to address as we move on. One of the interesting things is, for example, I failed to make the point that, for example, for our digital collections, we are starting to minting DOIs, and that I think that that's going to help a lot for future ethical processes and proper referencing of data. That those digital object identifiers are going to play a key role, and also the open data philosophy still not fully permeated throughout many of the scientific activities. So also very few federal agencies do have freely and openly accessible repositories, and I do mean open and free. That means no no passwords, no asking permissions for getting into the data. And I think that the CONACYT still does not have a clear mandate for open data in all of their approaches. So I think that that's something that needs to be addressed. And finally, I think that this diversity into IT areas and medicine applications or geoscience applications or social applications, this diversity should be our strength and not our weakness. So that's all. Thank you very much for your attention.
We are going to make an exception because he is remotely speaking and I don't know if he's going to stay for the rest of the conference. If you want to ask questions to Enrique, please let me know right now.
This is Carlos García, Enrique. I think we can contribute to the project at least two ways. One of the things that probably we can work together is that we have approximately 500 campuses throughout Mexico that have good connectivity. And I think it should be possible to install data stations in all 500 campuses. No? Basically, what we need is to give incentives to the campuses that there is a scientific project in which we can all collaborate by having access to the data and by probably being able to monitor their local stations and derive local applications from their data. No? I don't know if campuses are the best sites in which to collocate these data stations, but I'm pretty sure that, I mean, the thing that it would be clear is that there will be no additional telecommunications costs. The data will be probably be sent at night, collected at night when there is low traffic, and I think it's a possible way to go. The other thing is basically the data infrastructure is something that we care a lot about. I think the infrastructure of interconnection, internet exchange points, that basically we're working upon. We've already started the Mexico City exchange points. It should be ideal to host these data repositories in the internet exchange points throughout Mexico, because this allows better connectivity for everyone that needs to have access to their repositories. So I hope that we can work together with you, and I hope this is helpful. No? Thank you.
Yes, no, I think that you raised a couple of very good issues. Our experience so far with state universities and other locations is that in many cases we scout locations for GPS sites, and we do have in mind that in many places we can use their local facilities and the local telecom infrastructure, the existing infrastructure. And in most cases, and I think that in all cases, once we approach the right person, everything works very smoothly, and everybody is very enthusiastic, and everybody is very willing to share their resources. But sometimes it's a problem that, and just until recently, I was able to get a to look into the Mexico Conectado site map, because there used to be a lack of information. So I think that we're moving very much in the right path, and I'm sure that CUDI and our project and other projects like ours, I think that we're going, in short, we're going the right route, I think, and it's just a matter that we have always, like I said, we always live and present and share our look for collaborations within our very small realms, and we do not look beyond that. And I think that, and that's why I really appreciate this invitation to share our project, because that opens a cadre of possibilities for us. And so I think that we are, now that we are starting to know each other, I think that we can do much better.
Muchas gracias, Enrique. Thank you very much. We have to move forward because we are already half an hour away from our original schedule. So I would like to thank Enrique and continue with the next